So, why does your teacher tell you that a pendulum only follows simple harmonic motion for small angles? Well, that will actually hopefully become clear in this derivation of a period of the pendulum. Let's start by looking at a pendulum of length L. When it moves out with some arbitrary displacement x from equilibrium at an angle theta, we can look at the forces at play. The only two forces acting on a pendulum are tension and gravity acting straight down, with tension acting along the string. The force of tension must be the same as this component of gravity, since there is no motion in that direction, so the net force on the pendulum is this force in the opposite direction of the displacement that plays the role of the restoring force, i.e. the defining feature of simple harmonic motion. This net force is equal to mg sine theta, from which we can see that the acceleration is g sine theta from F equals ma. Then, using the definition of simple harmonic motion, the acceleration being equal to the negative of the angular velocity squared times the displacement from equilibrium, we can see that g sine theta equals negative omega squared theta. X is the arc length of the circle, which is the radius of the circle times the angle in radians. The radius is just equal to the length of the pendulum, so we can substitute that in. We can then rewrite omega as 2 pi over t, which is the definition of angular frequency, expand the brackets, and rearrange for t. We're now almost there, but are left with this odd theta over sine theta that you don't see in the final formula. This is dealt with using limits, specifically that as theta approaches 0, theta over sine theta approaches 1. So, for small angles, we can use this simplified formula as an approximation. Thanks for watching, and if you're interested, I have a few other derivation videos that you can check out on the screen now.